Hello everyone, today let's take a look at QP168, where you toss a fair coin n times and you record the sequence, and then a run's just defined as a consecutive sequence of identical outcomes. So for example, in this sequence right here, we have 4 runs, this HH at the beginning, then these 3 T's in the middle, then this H, and then this T at the end. So in part A, we want to find the formula for the expected number of runs after n flips. So if we let x be basically what we're trying to find, the number of runs after n flips, we're trying to find the expected value of x. So if we just look at a random sample, let's say we flip it 9 times here, and then we get 3 H's at the start. That's going to be our first run, right? And then we're going to get 3 tails here. We're going to get 2 heads and then 1 tail at the end. That's going to give us 4 different runs. But how do I know what a run is? Well, it's basically when I'm going to have an H followed by a T or a T followed by an H, right? When it flips. So at this point right here, it flips from an H to a T. And then at this point right here, it flips from a T to an H. And then at this point right here, it flips from an H to a T. So this flipping point right here separates this run, the first run, from our second run. This flipping point right here separates this second run from this third run, and this flipping point here separates this third run from our fourth run. So our number of runs x, we can basically just define that as our first run, and then we can just add on all of the flipping points, right? So here I've added on y, which is basically the number of flipping points, and in our case we'd have 3 flipping points, and then we add on 1, so that's going to give us 4 different runs. So this is going to work. So linearity of expectation, the expected value of x is just going to be 1 plus basically the expected value of y, the expected number of flipping points in our sequence of n flips. So expressing it this way is going to make life a lot easier, because now I don't have to do a big combinatorial sum like I'd have to do if I wanted to calculate this straight up, which I'll probably do at the end of the video as just another way to solve this problem. But now the expected value of y is going to be much easier to find, because we can express it as basically a sum of indicators. So how can we do that? Well, basically for all my possible flipping points in my sequence, so maybe this one right here, I'm going to call that one I sub 1, and then I'll call the flipping point from this one to this one, I'll call that I sub 2, and then I'll call this one I sub 3, and all of these are going to be equal to 1 if basically there is a flip, or they're going to be equal to 0 if there's not a flip. So just like we've been doing for all these linearity questions with the indicators, we can express y as a sum. I'll call our indicator, or our iterator, j. It's going to be going from 1, and then how many different flipping positions do we have in a sequence of n runs? Well, in our case, when we had 9 runs, I basically have 8 different flipping positions, right? Because I have 3 here, and then I have 4, 5, 6, 7, and 8. So if I have n h's and t's in my sequence here, then I have n minus 1 basically possible flipping positions, right? And a flipping position is just when it goes from heads to tails like it does here, or it goes from tails to heads like it does here. So I'm going to be summing up over all of these I sub j. So I'm just going to be looking at this one. I'm going to say, did the sequence flip here? No, it didn't. Did our sequence flip here? No, it didn't. So those are going to be equal to 0, those 2 indicators. And then when I get to this one, it did flip. So that indicator is going to be equal to 1, right? And then this one would be 0. And that one would be 0, and then this one would be 1. This one would be 0 here, and then this one would be 1 here, so it would give us 3. And then just like we've been doing a million times, you know the drill, right? The expected value of y, linearity of expectation, we can just bring that inside of this sum, and we're just going to be summing up over the expected value of all of these indicators, regardless of dependence or independence. We can do that. And now the expected value of one of our indicators, I sub j, well, that's just going to be equal to the expected value of an indicator is just equal to the probability that that indicator is equal to 1. So now what's the probability that one of our indicators is equal to 1? So what's the probability that in a given position in our sequence that it is a heads followed by a tails, or a tails followed by a heads? Well, there are 4 possible outcomes that I could have, right? I could have a heads followed by heads, I could have a tails followed by a tails, I could have a heads followed by a tails, or I could have a tails followed by a heads. So 2 out of 4 of these are going to make our indicator 1, and the other 2 are going to make it equal to 0. So the probability that's equal to 1 is just 2 divided by 4, which is 1/2. So this is just going to be 1/2. So I'm just going to be summing up here for the expected value of y. I'm going to be summing up 1/2 n minus 1 times. So that's just going to be n minus 1 divided by 2. So the expected value of y is n minus 1 divided by 2. The expected value of x, which is what we were trying to find, is 1 plus n minus 1 divided by 2. So the expected value of x, let's just write it out, is going to be 1 plus n minus 1 divided by 2. 1 is just 2 divided by 2, so we're going to have 2 divided by 2 plus n minus 1 divided by 2, and that's just going to be equal to, if I can get my pen to work, it's going to be equal to n plus 1 divided by 2, which is our final answer. And now once you know that, part B is going to be very simple. It's just going to be plugging in n equals 100 into this formula right here, which will give us 101 divided by 2, which is just equal to 50.5. So again, this expected value calculation made much simpler just by the fact that we can express it as a sum of indicators and use linearity of expectation, right? It's going to make it a lot simpler. If we wanted to calculate the expected value of x straight up, just using combinatorics would be a lot harder. But if we did want to do it that way, the expected value of x, just by definition of expectation, is the sum over all the possible values that x can take, and take values from 1 up to n, because we could have one run in the case where we have basically all h's or all t's, or you could have n different runs in the case where it alternates ht, 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 ht for the entire sequence. And then we're going to sum up basically of x times the probability that x is equal to that little value of x. So now we just need to find this probability distribution right here. So for this probability distribution right here, well, we know the total number of ways that we could get a sequence is just going to be 2 to the power of n. If we flip a coin n times, each coin has 2 different outcomes, so 2 to the power of n total. Then we can start working out some probabilities. The probability that we have exactly one run is just going to be either we have all t's or all h's, right? There's only going to be one way to have all h's, and there's only one way to have all t's. So there's two ways to have all h's or all t's, so the probability is going to be 2 divided by 2 to the power of n, our total. Now let's look at the probability that x is equal to 2. Well, that's going to be the probability that we have exactly 2 runs. So we have 2 different cases for this, right? If we start our sequence with an h, right, and we have a bunch of h's, let's just say we have a ton of h's, and then at some point we're going to have some flipping point, right? And then it's going to become a bunch of tails. If we start with h's, or we could start with tails, and then we're going to have eventually some flipping point and then a bunch of h's after that. And then we have n minus 1 possible different flipping positions in our sequence of n, right? We already talked about that. And then we're just going to need to choose one of those positions to be the actual flipping position. So we have n minus 1 choose 1 choices for our flipping position. So n minus 1 choose 1, and then we could start with h's or we could start with tails, right? Those are our 2 different situations. So we have to multiply that by 2, and then we're going to divide that by 2 to the power of n. So that's the probability that we have exactly 2 runs. And then you can keep going. The probability that we have exactly 3 runs, well, there's going to be what sequences can we have? Well, we can start with h's. Let's say we start with h's, then we're going to have some flipping point where it's going to be a bunch of tails, and then we're going to have another flipping point, and we're going to go back to h's. Or we could have a start with tails, a flipping point, then a bunch of heads, and then a bunch of tails after another flipping point. So we have 2 different possible types of sequences, those that start with h's and those that start with t's. So 2 times, and then we're choosing basically 2 out of these n minus 1 flipping positions to be our actual flipping position. So n minus 1 choose 2 divided by 2 to the power of n. And now the pattern's obvious, right? The probability that x is equal to little x is just going to be equal to 2 times n minus 1. Basically choose x minus 1 and then over 2 to the power of n. So that's just equal to, when we cancel a 2 from the top and bottom, that's just going to be n minus 1 choose x minus 1 divided by 2 to the power of n minus 1. And then we can just plug that in and use some type of combinatorics to basically simplify this sum. So if I cross out all this stuff to make some room now that we've figured out basically our probability distribution or a formula for it, I'm going to just plug this in instead of this right here. We're going to have this be our probability, and now we need to figure out this sum. So once I pull out this constant, this is what we have right here. Now the problem is we're going to have to find some type of identity that's going to make this simpler, which is the problem with doing it this way, is why linearity of expectation is so much simpler. But basically, if we want to keep on going this way, what I could do is basically I have to do a substitution just to make it simpler. Let's say k equals x minus 1, then we could replace this x minus 1 with this k. We could replace this x here with basically k plus 1, right? Then when x would be equal to 1, k would be equal to 0, and then when x would be equal to n on the top, we'd have k equals n minus 1. So k would be going from 0 to n minus 1 in our sum now. When I distribute this over this inside here, then I get this equation over here. We know that this term right here from QP66, that's just going to be 2 to the power of n minus 1. That comes from the binomial theorem, and now to do this one, we can also use the binomial theorem. Basically, we know from the binomial theorem that 1 plus x to the power of n minus 1 is equal to this sum right here, which looks awfully similar to this one. We just need to get that k out front, which we know we can do just by taking the derivative of both sides. So when I take the derivative with respect to x of both sides, I get this k down in front right here, and basically all we have to do now is just to multiply each side by x to match the powers. When I do that, I'm going to get this. And then we can just evaluate this at x equals 1 to get rid of this right here, and then when we plug in 1 over here, we just get 1 plus 1 to the power of n minus 2. We made this a 1 as well, so this right here is the exact sum that we want. It's just going to be equal to n minus 1, and then this is going to be 2 to the power of n minus 2. So we substitute that in for the green part right here. When we do that, we get 1 over 2 to the power of n minus 1 times basically n minus 1 times 2 to the power of n minus 2 plus 2 to the power of n minus 1. And then distributing this, when we multiply these two together, we get n minus 1 divided by 2. When I multiply this one by this one, I just get 1. So n minus 2 divided by 2 plus 1. And again, that's just going to be equal to n plus 1 divided by 2. So you can see we get the exact same answer. It's just going to be a lot more complicated, and there's no need to do it this way when we could just use linearity. So the final answer for part A is n plus 1 divided by 2, the expected number of runs when we flip n coins. And then when we have n equals 100, so we flip 100 coins, we got that basically when we plugged in 100 into our formula, we got 50.5 for the expected number of runs. So that's the answer for part A, and this is the answer for part B.